Hi, this is the Handcycle leg carrier's technical video draft. We will be presenting our technical design by dividing our device into three subsystems. The outer shell subsystem will be presented by Karen and Jacob, the attachment subsystem will be presented by Kyle, and the inner shell subsystem will be presented by Amir.
The first subsystem that we worked on for our device design was the outer shell subsystem. In order to create a device that fits our client's needs, it was important to take into consideration the shape, orientation, fabric, and sealing mechanism of the outer shell. In order to create the shape of the carrier, it was important to take into consideration the type of handcycle Rosemary uses. Currently, Rosemary uses a top-end accelerator XLT Pro handcycle with very little storage space to add a prosthetic leg carrier. In fact, the only storage space on this handcycle itself is the space behind the seat. Thus, in order to use this space, the carrier was created into the shape of a triangle in order to fit it in between the parallel bars that frame the back of the seat without hitting the rear tires. The shape of the carrier was also decided due to the limited orientation of the prosthetic leg. The prosthetic leg that Rosemary employs is an Autobox Genium 3B1 model with limited band movement and ankle flexion. Due to this fact, the shape and orientation of the outer shell was designed to suit this limitation. As you can see from the picture within the slide, the triangle shape of the carrier accommodates the limitations to Rosemary's prosthetic leg.
When choosing fabric for the outer shell, we needed to keep a few things in mind. The chosen fabric had to meet our objective of being lightweight, durable, and waterproof. We found the Ottertex Canvas waterproof fabric sold by FabricWholesaleDirect.com met all of our objectives. It is made of 100% polyester with a PVC coating to make it waterproof. The weight of this fabric is approximately 1.1 pounds per yard, and being that we had to keep the weight limit of 8 pounds for the carrier, the best choice of material to keep it lightweight would be the PVC coated polyester.
Once the fabric was decided, it was important to determine which stitching orientation was most ideal for our carrier before sewing. To do this, we conducted a load cell test based on the American Society for Testing of Materials using a heavy-duty, high-strength polyester thread. Our group tested a straight stitch, a zigzag stitch, and a zigzag pattern with a straight stitch. Based on the control sample, it was determined that a tear before the narrow cross-sectional area of the fabric was due to mechanical property of the material failing and not the stitching orientation. All other tears were due to the stitching pattern failing. When the test was completed, the average Young's modulus was taken for each stitching orientation. Although the zigzag stitch appeared to have the greatest Young's modulus, the straight stitch had the highest average yield point, meaning its point of permanent deformation was higher than any other stitch. It also still had a relatively high average Young's modulus. Thus, the straight stitch pattern was chosen.
After determining which stitch orientation to use, we had to create a sewing guide that wouldn't be troubling to follow and that could be replicated for future use. To do this, we created the guide shown that takes one overall piece of fabric that is 47.86 inches in length, with the width being the standard for how the fabric is sold at 60 inches. On this template, one can see that the 5 pieces to cut out are labeled with letters. Then each edge of each piece is color-coded to correspond to what edges need to be sewn together. The instructions to follow are also shown. One thing to note is that the piece labeled D needs to be cut in half at the middle of the shorter edge measured at 9.50 inches. The cut will be at the 4.75 inch mark on that edge and is also where the waterproof zipper will be attached. Our design for the outer shell incorporates a waterproof zipper. This zipper was purchased from Amazon and was dimensioned at 31 inches long with a width of 1.26 inches. This didn't require any alterations as we needed it to be 31 inches to center for our carrier design. This zipper feature allows for ease of access when a user interacts with the carrier and provides a secure way to close the carrier. The orientation for our first prototype opened from the bottom of the carrier to the top of the handcycle seat. However, later iterations of our design will reverse the orientation. By doing this, a user could open the carrier from their seat and a cord could be attached to the zipper to enable a user to close the carrier without the need to leave their seat.
The second subsystem that we worked on was determining the right attachment components for the carrier. To accomplish this, we had to consider options that permitted size versatility, ease of use, attachment strength, and independence of different weather conditions. By conducting product exploration of existing bicycle attachment mechanisms, we came across rubber pull straps that are used on bicycle headlights and taillights. We decided to use these rubber pull straps because they seemed to fit all of the criteria we needed for an appropriate attachment mechanism. They look simple to use and seem relatively common in the cycling community. In order to test the capabilities of these attachment components and see if they would be applicable for our device, we conducted various physical tests to ensure their suitability. First, we conducted load testing on these straps to determine the peak load that the straps could endure. We tested one strap at a time and got the following results shown to the right. The mean peak load force was about 85 newtons. This value has doubled since we used two straps on the device to obtain a total peak load strength of about 170 newtons. As determined before, the carrier is meant to hold a max weight of 20 pounds or 88.97 newtons. Our combined result of 170 newtons is substantially greater than the 88.97 newton load force that the carrier is designed for. We can then conclude that the load strength of the pull straps is sufficient for our device. The violin plot to the right also displays the distribution of the data, demonstrating the most common results were close to 85 newtons. Next, we had to confirm the grip strength of the attachment components to make sure the carrier does not slide away from its original position. We decided to test both dry and wet conditions based on the weather patterns of our client's location. We tested this by determining the attachment component displacement between the loaded and unloaded conditions for both dry and wet frame bars. The results demonstrated that there was no movement for either condition except for a 0.5 centimeter change in trial 4 of the wet condition. This test setup was extreme, and such a small change was determined to not be detrimental to the function or safety of the device. These results allowed us to conclude that the carrier and its contents would be secured in a stable position with these attachment components.
The last subsystem we present is the inner shell. The primary objective met from this is that the interior of the carrier will be soft and cushioned. Additionally, this will allow our device to have some structure and be somewhat rigid, as the fabric alone is flimsy. To create this, we will use a high-density foam cushion, shown in this picture, which was retrieved from the posting by the Foamers Company on Amazon. The manufacturer explains that the foam has a compression rate of 44 pounds. That means that it can withstand up to that much weight in order to press down on the foam, compressing it to 25% of its original thickness, and allow it to bounce back to regular size after the weight is removed, without any deformation to the foam. This is useful for us because Miss Salek's prosthetic is actually 9 pounds, which is significantly less than the compression rate, so the interior would not be damaged. Additionally, despite using all the foam, the total weight of the carrier was only around 700 grams, allowing us to maintain the lightweight characteristic. On the top left-hand corner, you will see the CAD drawings done for the stencils to cut out the foam pieces. Below it is another drawing which shows how each foam piece will be inserted. Examining this, it is seen that there will be one layer of an A cutout, one on each side of the device. Then there will be two layers of a B and C cut. The reason for this is that the former comes into contact with the rear frame of the Handcycle seat, while the latter piece rests above the bottom beam. Hence, we want to mitigate forceful contact that the prosthetic or any other device that might be in the carrier will have with those parts of the Handcycle. Additionally, D cutouts will be placed on top of the A piece to provide padding against the two parallel beams of the frame. On the right, you can see what the inside looks like when the students finish, as well as how the carrier looked once all subsystems were intact and the device was on the Handcycle. Finally, we wanted to test a secondary objective and see whether this truly was aerodynamic. To do this, we conducted a test where we used two riders, one who weighed 235 pounds and another who was 135 pounds, and examined whether we failed to reject or reject our null hypothesis, which says that there is no difference between the average speed of the Handcycle with and without the carrier. The p-value obtained for both riders was greater than our critical value of 0.05, hence we failed to reject our null hypothesis as there is no significant difference between the speeds. Hence, in addition to the profile of the carrier, this test helps us see how the drag remains negligible.